Today, the world looks to the sky with a mixture of anticipation and trepidation. The world is turning its gaze skyward with a mix of anticipation and unease. An interstellar object known as 3I/Atlas, also designated as C/2025 N1 Atlas, is hurtling through our solar system at a staggering speed of 58 kilometers per second, faster than any object we have ever observed in such proximity. But the question on everyone's mind is this: when will it make its closest approach to Earth? The answer is the 19th of December in the year 2025, at a safe distance of 1.8 astronomical units, which translates to approximately 270 million kilometers. Rest assured, it poses no threat of collision with our planet, but this proximity is close enough for telescopes like the James Webb Space Telescope and the Hubble Space Telescope to gather invaluable data that could unlock secrets about its extraterrestrial origins. Imagine this: a visitor from interstellar space, potentially carrying clues to alien life or advanced technology. This is not science fiction. It is the reality unfolding before us. Discovered on the 1st of July in the year 2025 by the Atlas telescope in Chile, 3I/Atlas has left scientists stunned with its immense mass of 33 billion tons and its peculiar chemical composition, abundant in carbon dioxide, with pure nickel vapor but a notable absence of iron, a rarity in natural cosmic bodies. Avi Loeb, the renowned professor from Harvard University, has even suggested that this could be evidence of extraterrestrial technology, as pure nickel is typically found in industrial alloys rather than in nature. Just recently, on the 25th of September, it narrowly escaped a coronal mass ejection from the Sun, an event that could alter its activity and provide even more insights as it nears its perihelion on the 29th or 30th of October. This is a historic opportunity for humanity to explore what lies beyond our solar system. We will be tracking it closely as it develops a potentially brilliant tale upon approaching the Sunday. Do not miss this. It is the opening chapter in the era of interstellar exploration. Let us delve deeper into what makes 3I/Atlas so captivating. This object is not just another comet or asteroid. It is the third confirmed interstellar visitor to our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Unlike its predecessors, 3I/Atlas stands out due to its hyperbolic orbit, which means it is not bound by the Sun's gravity and will eventually exit our system forever, heading back into the vastness of the Milky Way. Its journey began from the direction of the constellation Sagittarius, a region of the sky that has long intrigued astronomers. Sagittarius points toward the center of our galaxy, a dense, stellar nursery where ancient stars and exotic phenomena abound. 3I/Atlas may have originated from the thick disk of the Milky Way, a region populated by older stars, perhaps ejected from its home system billions of years ago through gravitational interactions with planets or other stars. The discovery itself was serendipitous. The Atlas system, designed primarily to detect near-Earth asteroids that could pose a threat, picked up a faint blip, moving at an anomalous velocity. Initial observations suggested it was something ordinary, perhaps a distant comet from the Oort cloud. But as more data poured in from observatories around the world, the truth emerged. Its speed at infinity, around 60 kilometers per second, far exceeded what could be explained by solar system dynamics alone. This hyperbolic excess velocity confirmed its interstellar nature. By the 14th of June, early sightings had been logged, but it was not until the 1st of July that the Minor Planet Electronic Circular officially designated it as an interstellar object. The excitement in the astronomical community was palpable. Telegrams and emails flew between institutions, and within days, major telescopes were redirected to study it. The Hubble Space Telescope captured its first images on the 21st of July, revealing a faint coma, a hazy envelope of gas and dust surrounding the nucleus, and a tail extending about 3 arc-seconds, visible only under high magnification. The James Webb Space Telescope joined the effort on the 6th of August, using its infrared capabilities to peer through the dust and analyze the chemical signatures. What it found was astonishing. A carbon dioxide to water ratio higher than any comet ever observed, suggesting the surface has been cooked by cosmic rays over eons of interstellar travel. This high carbon dioxide content could mean explosive outgassing as it warms near the sun, potentially leading to a spectacular display in the night sky come October. But the real intrigue lies in its metallic composition. Spectroscopic analysis from the Very Large Telescope in Chile detected atomic nickel vapor in the coma, with production rates between 10 to the power of 23 and 10 to the power of 24 atoms per second, even at a distance of 2.85 astronomical units from the Sunday. Normally, nickel sublimates only when much closer to a star, but here it is evaporating prematurely. More puzzling is the near absence of iron. The nickel-to-iron ratio exceeds 1, whereas in typical solar system comets, it is less than 0.1. This anomaly has sparked debates. Is it a natural phenomenon? Perhaps from nickel tetracarbonyl compounds formed in a carbon-rich environment? Or something more exotic? Avi Loeb, known for his bold hypotheses about Oumuamua, has weighed in publicly. In interviews and papers, he posits that the pure nickel could indicate artificial construction, akin to materials used in spacecraft or probes. Nature does not produce pure metals like this in such quantities, he argues. It resembles the alloys we engineer on Earth. While the majority of scientists favor a natural explanation, perhaps originating from an asymptotic giant branch star, where carbon and heavy metals are forged in abundance, Loeb's ideas have ignited public imagination. Could this be a relic of an alien civilization, a probe sent to scout distant systems? Adding to the mystery, 3I/Atlas exhibits an anomalously large mass. Estimates place it at 33 billion metric tons, far heavier than expected for its size, which ranges from 0.44 to 15 kilometers in diameter depending on albedo assumptions. This density implies a composition denser than ice or rock, perhaps with a metallic core. Furthermore, there is minimal non-gravitational acceleration detected, which is unusual for a cometary body. Typically, outgassing jets would perturb the orbit slightly, but here the path remains steadfastly predictable. Its retrograde orbit, inclined at 175 degrees nearly opposite to the plane of the planets, further sets it apart. This means it is moving against the flow of the solar system, increasing the relative speed of any potential encounters. On the 3rd of October, it will pass within 0.2 astronomical units of Mars, close enough that Martian orbiters might capture detailed images if positioned correctly. Then, on the 19th of December, its Earth flyby at 1.8 astronomical units will offer the best viewing opportunity. From our vantage point, astronomers are mobilizing global resources. The European Southern Observatory, NASA, and the European Space Agency have coordinated observation campaigns. Amateur astronomers with backyard telescopes may even spot it as a faint streak in the pre-dawn sky by late November, assuming it brightens as predicted. Models suggest it could reach magnitude 8 or brighter near perihelion, visible through binoculars under dark skies. The implications of studying 3I/Atlas extend far beyond astronomy. If it carries organic molecules or unusual isotopes, it could provide clues to the chemistry of distant star systems, perhaps even the building blocks of life. Its age, estimated at 7 to 14 billion years, predates our solar system, offering a snapshot of the early Milky Way. And if Loeb's speculations hold any water, it could redefine our place in the cosmos, proving we are not alone. But let us not forget the recent brush with the coronal mass ejection. On the 25th of September, a massive solar flare erupted, hurling plasma toward the object's path. Initial reports suggest it grazed the edge, potentially stripping away surface layers and enhancing outgassing. This event underscores the dynamic nature of space. Even interstellar travelers are not immune to the sun's temper. As we approach the perihelion in late October, expect more revelations. Will it fragment like some comets do, scattering debris across the inner solar system? Or will it hold together, its secrets intact, as it slingshots away? One thing is certain. 3I/Atlas is a harbinger of more to come. With improved detection technologies, we may soon discover dozens of such visitors annually, each a messenger from the stars. In the meantime, the closest approach on the 19th of December serves as a reminder of our fragile yet wondrous position in the universe. It is a call to look up, to wonder, and to prepare for the unknown. This interstellar enigma is not just passing through. It is inviting us to expand our horizons, to question what we think we know about the cosmos. The story of 3I/Atlas is still unfolding, but its legacy may endure for generations. From the moment of discovery to its farewell departure, it challenges our understanding of space, time, and possibility. As humanity stands on the cusp of this new frontier, let us embrace the mystery with open minds and vigilant eyes. To truly appreciate the scale, consider the distances involved. 1 astronomical unit is the average distance from Earth to the Sun, about 149 million kilometers. At one point, 8 astronomical units, 3I/Atlas, will be farther than Mars at its closest, but nearer than Jupiter. This positioning allows for multi-wavelength observations: optical for the tail, infrared for the heat signature, and radio for any potential emissions. Scientists are particularly eager to monitor for signs of activity beyond the coma. If it ejects material asymmetrically, it could spin up or alter course slightly, providing data on its internal structure. Moreover, the high speed means any ejected particles would carry immense kinetic energy, potentially creating micrometeor showers if they intersect Earth's orbit in the future, though calculations show this is unlikely. Public engagement has surged. Social media is abuzz with hashtags like #InterstellarVisitor and #AtlasComet, with artists rendering dramatic visualizations and educators hosting webinars. Schools are incorporating it into curricula, teaching orbital mechanics through real-time tracking apps. In a broader context, 3I/Atlas highlights the importance of international collaboration in space science. Data sharing between observatories in Chile, Hawaii, and Europe has been seamless, demonstrating how unified efforts can accelerate discovery. As we count down to the 19th of December, the anticipation builds. What will we learn? Will it confirm our theories or upend them? One certainty amid the unknowns: this object is a bridge between worlds, a cosmic envoy reminding us that the universe is vast, ancient, and full of surprises. Let this be the hook that draws you in. On that fateful day in December, as 3I/Atlas graces our skies from afar, humanity takes another step toward unraveling the tapestry of existence. Stay tuned. The journey has only begun. Picture the vast, star-studded expanse of the southern hemisphere sky on a crisp night in Chile. It is the 1st of July in the year 2025, and at the Atlas Observatory atop Mauna Loa, a network of robotic telescopes scans the heavens relentlessly. These instruments, part of the Asteroid Terrestrial Impact Last Alert System, are built to spot potential threats from space rocks that might one day endanger Earth. But on this particular evening, something unexpected flickers into view. A dim speck of light moving in a way that defies the usual patterns of solar system objects. Labeled initially as A11PL3Z, this anomaly does not follow the elliptical paths of comets or asteroids bound to our Sunday. Instead, its trajectory hints at origins far beyond, from the cold voids between stars. As data streams in from the twin telescopes, one in Hawaii, the other in Chile, the anomaly begins to reveal its secrets. The object's velocity clocks in at around 61 kilometers per second relative to the Sun, a speed that screams interstellar traveler. Within hours, astronomers at the University of Hawaii, who oversee ATLAS, alert the International Astronomical Union. Preliminary calculations show a hyperbolic orbit with an eccentricity greater than one, definitive proof that this visitor is not native to our cosmic neighborhood. By the next day, the Minor Planet Center issues a circular, designating it as C/2025N1 ATLAS. But whispers among experts already dub it 3I/Atlas, the third confirmed interstellar object. What sets this discovery apart is not just the speed or the path, but the sheer scale of the object. Early estimates from brightness measurements suggest a nucleus spanning anywhere from 0.44 kilometers to as much as 15 kilometers across, depending on how reflective its surface proves to be. That is larger than many known comets in our system, like the famous Halley, which measures about 15 kilometers at its widest. If the upper end holds true, 3I/Atlas could rival the size of small moons, packing a mass potentially in the billions of tons. Such bulk implies resilience, a body that has endured the harsh radiation and particle bombardment of interstellar space for eons. Observations ramp up quickly. On the 14th of June, retroactively identified as the first sighting in archival data, the object appeared as a mere streak on plates from other surveys. But by the 21st of July, the Hubble Space Telescope swings into action, its venerable mirrors capturing the first high-resolution glimpses. Hubble reveals a faint coma, that ethereal cloud of gas and dust enveloping the core, stretching out like a ghostly aura. The tail, though subtle at 3 arcseconds long, hints at sublimation, the process where ices turn directly to vapor under the sun's warming gaze. These features mark it as cometary in behavior, yet its composition teases at something more exotic. Enter the James Webb Space Telescope on the 6th of August, peering in infrared wavelengths that penetrate the dust veil. Webb's instruments detect signatures of carbon dioxide dominating the outgassing, with ratios to water vapor far exceeding anything seen in solar system comets. This excess carbon dioxide suggests a surface altered by billions of years of cosmic ray exposure, where volatile ices have been preferentially eroded or transformed. Nickel lines appear in the spectra too, unusually prominent without the expected iron companions, sparking immediate curiosity. Could this be a relic from a distant stellar forge, where heavy elements were synthesized in ways unfamiliar to our local chemistry? Tracing back, the story of 3I/Atlas echoes the serendipitous finds of its predecessors, but with unique twists. Recall 1I/Oumuamua, spotted in 2017 by the Pan-STARRS telescope in Hawaii. That cigar-shaped wanderer tumbled silently through, showing no coma or tail, its reddish hue suggesting organic tholins baked by interstellar radiation. Then came 2I/Borisov in 2019, discovered by amateur astronomer Gennady Borisov. in Crimea. Borisov behaved like a classic comet, sprouting a tail rich in cyanide and diatomic carbon, its hyperactivity linked to high carbon monoxide content. 3. I/Atlas bridges these worlds. Active like Borisov, yet enigmatic like Oumuamua in its chemical quirks, its retrograde motion travelling opposite to the planet's orbits adds a layer of intrigue, as if it were defying the solar system's established order. This inclination of 175 degrees means it plunged in from nearly the opposite side of the ecliptic plane, a path that maximizes relative speeds and minimizes lingering interactions. The night of discovery at Atlas unfolds like a detective novel. Technicians monitoring the feeds notice the anomaly around midnight local time. Alarms ping as algorithms flag the motion. Too fast for a main-belt asteroid, too straight for a perturbed Oort cloud object. Emails fly to collaborators worldwide. By dawn, orbital fits confirm the hyperbolic nature. With a semi-major axis that is negative, a mathematical hallmark of unbound trajectories. The excitement builds as more observatories join. The Very Large Telescope in the Atacama Desert turns its gaze, capturing spectra that affirm the interstellar label. This find resonates with historical echoes. Think of the WOW signal from 1977, that brief, intense radio burst from Sagittarius, the very direction 3I/Atlas approaches from. Coincidence? Perhaps, but it fuels speculation. Was that signal a beacon from the object's origin system, or mere noise? No direct link exists. Yet the alignment tickles the imagination, suggesting our galaxy teems with activity we are only beginning to glimpse. As weeks pass, the object's brightness evolves. Initially at magnitude 20, it brightens steadily as it closes in from 4.2 astronomical units at discovery. Projections indicate it could peak at magnitude 8 near perihelion, a glow visible through modest telescopes. Amateur astronomers gear up, plotting ephemerides to track its passage across constellations. Deeper analysis reveals the nucleus's potential irregularity. Photometric variations suggest rotation, perhaps every few hours, causing brightness fluctuations that map to an elongated shape not as extreme as Oumuamua's 10:1 ratio, but enough to imply a fractured history. Maybe gravitational tides from a close stellar encounter sheared it, or collisions in its birth cloud left scars. The chemical profile deepens the mystery. Beyond carbon dioxide and nickel, traces of cyanide appear, common in comets, but here in ratios skewed toward heavier isotopes. This isotopic fingerprint could pinpoint the object's natal environment, a metal-poor star in the galactic thick disk, where nucleosynthesis favors certain pathways. Age estimates place it at 7 to 14 billion years, predating our Sun by billions, making it a time capsule from the galaxy's youth. Collaborative efforts amplify the study. The European Space Agency coordinates with NASA, sharing data from ground-based radars that bounce signals off the object, refining size and shape. No artificial signals emanate. No repeating patterns that might suggest technology, but the silence itself intrigues. If natural, it exemplifies the diversity of interstellar nomads. If not, well, that opens Pandora's box. Public fascination grows organically. Forums buzz with theories. Is it a fragment of a disrupted planet? A rogue worldlet ejected during stellar formation? Or, as some fringe voices claim, a derelict probe from an ancient civilization? Mainstream science tempers this, emphasizing natural explanations, yet acknowledges the value in questioning. By mid-August, 3I/Atlas has crossed the orbit of Jupiter, undisturbed by the gas giant's pull due to its velocity. This passage offers a natural experiment, Gravitational perturbations, if any, could reveal internal mass distribution, none detected so far, reinforcing the massive core hypothesis. The discovery's ripple effects extend to policy. Funding for sky surveys surges, with calls for dedicated interstellar object hunters. Projects like the Vera C. Rubin Observatory, set to come online soon, promise to spot dozens more annually, transforming rarity into routine. Yet, amid the data deluge, a sense of wonder persists. 3I/Atlas is not merely an object. It is a narrative unfolding in real time, challenging assumptions and inviting deeper inquiry. Its path from obscurity to spotlight mirrors our own quest for understanding, starting as a faint signal, growing into a beacon of cosmic insight. As it hurtles inward, questions multiply. Will warming reveal more volatiles? Could organics hint at panspermia, the seeding of life across stars? Or will it simply grace our skies, a fleeting reminder of the galaxy's grandeur? This interstellar interloper, born in distant fires, now weaves through our domain, offering glimpses of worlds unseen. Its story, from that initial detection to ongoing scrutiny, underscores the thrill of exploration, the unexpected find that reshapes our view of the universe. To grasp the essence of 3I/Atlas's journey, envision the solar system not as a static clockwork of planets and moons, but as a grand arena where gravity plays the role of an indifferent host. This interstellar intruder slices through that arena on a hyperbolic curve, a mathematical grace note that defies the closed loops of our familiar orbits. Hyperbolic paths are the signatures of escapees, objects with enough velocity to ignore the sun's pull and vanish back into the galactic wilderness. For 3I/Atlas, this curve boasts an eccentricity of about 6.139, a number that screams freedom from our stellar bonds. It is not circling back like Halley's comet. It is a one-way ticket through our neighborhood, arriving from the infinite and bound for the same. The trajectory begins in the depths of space, far beyond the Oort cloud's icy fringe. Approaching from the constellation Sagittarius, it hurtles inward at 60 kilometers per second, a pace that would outrun any human-made probe. When first spotted at 4.2 astronomical units, roughly the distance of Jupiter's orbit, it was already committed to this daring dash. Crossing that giant planet's path offered no detour. Jupiter's gravity, mighty as it is, barely tugs at such a speed demon. Instead, 3I/Atlas presses on, its path a shallow arc, bent only slightly by the sun's distant embrace. As it dives deeper, the perihelion awaits the closest brush with our star. This pivotal point falls in late October, at 1.36 astronomical units, placing it just inside Mars's average orbital radius. Here, the sun's heat intensifies, potentially awakening dormant ices and gases trapped in its core. Imagine the nucleus, perhaps 5 kilometers wide, beginning to fizz like a cosmic soda can shaken too hard. Carbon dioxide, dominant in its makeup, could erupt in plumes, sculpting a tail that stretches across the sky. Yet, unlike typical comets that fragment under such stress, this object's colossal mass, estimated in the billions of tons, suggests resilience, a steadfastness that keeps its course true. Post-perihelion, the adventure escalates. Early in October, it skims within 0.2 astronomical units of Mars, a cosmic near-miss that could stir the red planet's thin atmosphere if any debris trails behind. Martian rovers and orbiters stand ready, their instruments poised to snatch data during this fleeting rendezvous. Will dust particles from 3I/Atlas pepper Mars's surface, leaving microscopic clues for future explorers? The possibility tantalizes, turning a routine flyby into a potential archive of interstellar history. Then comes the Earth encounter in mid-December, at 1.8 astronomical units. From our perspective, this is the prime viewing window, when the object might glow at magnitude 8, a faint but binocular accessible smudge against the stars. Its position then, farther out than Mars but closer than Jupiter, optimizes observations without risk. Telescopes worldwide will synchronize, capturing spectra that decode its secrets. But the path does not end there. After grazing our vicinity, it veers outward, aiming toward the constellation Gemini. This exit trajectory carries it beyond Neptune's realm, accelerating as gravity slingshots it away, never to return. What makes this orbit truly mesmerizing is its retrograde tilt, 175 degrees inclined to the ecliptic plane. Most solar system bodies spin counterclockwise from above the North Pole, a legacy of our disk's formation. 3 I/Atlas bucks that trend, racing clockwise like a rebel swimmer against the current. This opposition heightens collision risks in theory. Though its velocity minimizes actual encounters, it is as if the object were designed to thread the needle, weaving through planetary gaps with precision. Diving into the orbital elements paints a fuller portrait. The argument of perihelion sits at 128 degrees, dictating the orientation of its closest solar approach relative to the vernal equinox. The longitude of the ascending node is 322 degrees, marking where it crosses the ecliptic from south to north. These parameters, drawn from recent circulars by the Minor Planet Center, stem from over 100 observations, spanning weeks. The inclination, that defiant 175 degrees, underscores its outsider status nearly polar and reversed. Curiously, there is scant evidence of non-gravitational forces tweaking this path. Comets often wobble from jet-like outgassing, but 3 I/Atlas holds steady, implying either minimal activity or an overwhelming mass that damps such effects. This stability fuels speculation. Is the core denser than expected, perhaps laced with heavy metals like the anomalous nickel detected? Or does an internal structure, maybe a layered composition from its birth system, anchor it against perturbations? Recent solar activity adds a wild card. A coronal mass ejection grazed its vicinity in late September, a burst of plasma that could strip surface layers or ignite fresh outgassing. If that interaction boosted the coma, we might see enhanced brightness sooner, altering visibility forecasts. Astronomers monitor for such shifts, using models to predict how solar wind might sculpt the tail into ion and dust streams, each revealing different facets of the object's makeup. Comparing this journey to human endeavors sharpens the awe. Our Voyager probes, launched in the late 1970s, crawl at 17 kilometers per second, destined for interstellar space after decades. 3 I/Atlas, by contrast, blasts through in months, a natural speedster unbound by fuel limits. It evokes tales of ancient mariners crossing oceans, but here the sea is vacuum, and the vessel is a rocky enigma forged in alien fires. Ponder the origins shaping this orbit. Ejected from a distant star system, perhaps during a planetary migration or stellar close encounter, it wandered the Milky Way's thick disk for billions of years. That region, home to older, metal-poor stars, might explain the chemical oddities. High carbon dioxide from carbon-rich environments, nickel without iron from unique nucleosynthesis. The hyperbolic shape emerges from that long drift, where a gentle nudge from passing stars set it on a collision course with our Sunday. As it traverses, interactions loom. Passing near Sao Hua in early October could gravitationally stir minor moons or dust rings, though subtly, For Earth, the December proximity offers no hazard, but immense scientific bounty. Radio telescopes might scan for unnatural signals, echoing searches from the early 21st century's SETI efforts. If silent, it reinforces nature's hand. If not, well, that flips the script. The exit phase intrigues equally. Accelerating outbound, it will cross Uranus's orbit by mid-next year, then Neptune's, fading from view. But its legacy lingers. Any shed material could seed the Kuiper belt with interstellar grains, blending galactic histories. Future missions might sample those, tracing back to 3I/Atlas's wake. This path's predictability stems from refined computations. Using data from global networks, models incorporate solar radiation pressure and potential Yarkovsky effects thermal thrusts from uneven heating. Yet, uncertainties persist. If outgassing ramps up unevenly, the orbit could wobble slightly, demanding constant updates. In broader strokes, hyperbolic orbits like this challenge our isolation. They remind that the solar system is porous, a way station in the galactic flow. Estimates suggest thousands such objects pass through annually, most undetected. With advancing surveys like those from mountaintop arrays in the southern hemisphere, we edge closer to cataloguing them, each a puzzle piece in the cosmic mosaic. Delve into the math for a moment. The semi-major axis, negative in hyperbolic terms, quantifies the energy excess. For 3I/Atlas, it equates to that 60 kilometers per second, at infinity enough to traverse the galaxy in mere millions of years. A blink in cosmic time. This velocity aligns with stellar motions in the thick disk, supporting its provenance. Speculation swirls around perturbations. Has it grazed other systems en route, accruing scars or passengers? Microbial life, hardy in radiation, could hitch a ride, testing panspermia theories. Or perhaps exotic ices, unknown here, sublimate in ways that reveal new physics. As perihelion nears, tension builds. Will the heat crack the nucleus, birthing fragments that scatter like cosmic confetti, or endure its retrograde sprint, a testament to endurance? Observers worldwide await, instruments tuned to capture every nuance. This hyperbolic odyssey, from Sagittarius ingress to Gemini egress, encapsulates wanderlust on a stellar scale. It probes not just space, but our curiosity's bounds, urging us to ponder what other drifters lurk unseen, each with stories etched in their arcs. The journey's poetry lies in its transience, a brief intersection of paths where an ancient nomad graces our skies, then fades. In that fleeting arc, we glimpse the universe's vast narrative, one hyperbolic curve at a time. In the annals of cosmic wanderers, few tales captivate like the contrasting sagas of 1I, Oumuamua, and 3I, divided by Atlas, two interstellar nomads that crossed our solar system's threshold, each whispering secrets from distant realms, yet diverging in ways that challenge everything we thought we knew about the void between stars. Oumuamua, the first to earn the interstellar badge back in the late 2010 seconds, arrived like a silent scout, a cigar-shaped enigma, tumbling end over end without a whisper of gas or dust to betray its passage. Discovered by chance during a routine sky survey in Hawaii, it measured perhaps a few hundred meters long, its elongated form evoking images of a fractured rock or something more contrived, with a reddish tint hinting at eons of radiation scarring. No coma bloomed around it, no tail streamed behind. It was inert, a ghost slipping through the inner system at a modest 26 kilometers per second, dipping as close as 0.255 astronomical units to the Sun before vanishing toward Pegasus. Contrast that with 3 I divided by Atlas, barreling in from Sagittarius like a juggernaut unleashed. This behemoth, spotted in early summer this year, dwarfs its predecessor in every dimension that matters. Where Oumuamua was a slender sliver, estimated at 100 to 400 meters, Atlas sprawls across 0.44 to 15 kilometers, a scale that borders on planetary fragments. But size alone does not capture the shock. Recent measurements peg its mass at a staggering 33 billion tons, outstripping Oumuamua by 3 to 5 orders of magnitude. Imagine stacking the Great Pyramid of Giza billions of times over. That is the heft we are dealing with, a density suggesting a core packed with materials far beyond icy fluff. Why such bulk? Could it be a rogue planetesimal, ejected from a chaotic birth around an ancient star, or something engineered to withstand the interstellar grind? Delve into their velocities, and the disparity sharpens. Oumuamua cruised with a hyperbolic excess of 26 kilometers per second, enough to confirm its outsider status but tame compared to Atlas's blistering 60 kilometers per second. That extra kick means Atlas bends less to the sun's gravity, its path a shallower curve through our system. Oumuamua, slower and closer, felt the pull more acutely, slingshotting out after a tighter loop. Atlas, by comparison, maintains a standoffish trajectory, perihelion, at 1.36 astronomical units, safely beyond Mercury's scorch zone, while Oumuamua braved the heat at 0.255 astronomical units, risking disintegration that never came. This distance gap hints at survival strategies. Oumuamua's lack of activity might stem from depleted volatiles, stripped away during its billion-year trek, whereas Atlas, potentially younger at 800 million years or so, retains enough to fizz with carbon dioxide-rich outgassing as it warms. Their orbital inclinations tell another story of rebellion. Both are retrograde, defying the prograde whirl of our planets, but Oumuamua's 122 degrees tilt feels moderate, next to Atlas's extreme 175 degrees, nearly flat but reversed, like a mirror image of the ecliptic. This near-polar opposition for Atlas amplifies its wrong-way vibe, increasing relative speeds with everything in its path and minimizing gravitational dalliances. Oumuamua, with its milder angle, wove closer to the plane, passing Earth at 0.16 astronomical units post-perihelion, a tantalizing flyby that sparked global frenzy. Atlas keeps its distance, closest to us, at 1.8 astronomical units in December, a safer berth that still promises spectacular data hauls from observatories. Eccentricities underscore the escape artistry. Oumuamua's 1.2 hints at a gentle nudge from its home system, perhaps a planetary kick or stellar flyby. Atlas's 6.139 screams a more violent eviction, maybe a supernova's blast or a black hole's slingshot, propelling it with energy that barely notices our Sunday. This stronger hyperbola means Atlas spends less time lingering, zipping through in months, rather than Oumuamua's extended visit. Vertical excursions in the galactic plane add flavor. Atlas ventures farther off the disk, up to 0.475 kiloparsecs, suggesting a thicker disk origin teeming with older stars, while Oumuamua hugs closer, tied to the younger thin disk. Chemical fingerprints deepen the intrigue. Oumuamua's spectra showed a barren, rocky facade, possibly coated in organic tholins complex molecules forged by radiation on nitrogen and methane ices. No gases escaped. No metals gleamed. It was a stoic traveler. Atlas flips the script with a coma alive with anomalies. carbon dioxide dominating water vapor in ratios unseen before, and nickel vapor without the iron body it usually pairs with. Production rates of nickel atoms hit 10 to the 23rd per second, even at 2.85 astronomical units, far from the sun's blaze where such sublimation typically kicks in. This pure nickel ratio over 1 to iron evokes industrial alloys more than natural dust, fueling whispers of artificiality. Oumuamua sparked similar debates with its odd shape and non-gravitational acceleration, attributed to outgassing we could not see. But Atlas's mass quashes such effects, its path unswayed by jets that should perturb a lighter body. Ages offer a temporal twist. Oumuamua clocks in at around 1 billion years, a relative youngster from the galaxy's bustling thin disk where stars still form. Atlas, potentially from the ancient thick disk, carries a patina of greater antiquity. Though some models peg it younger at 800 million years, its composition screams exposure to harsher, older environments. This could explain the cooked surface, cosmic rays over eons eroding volatiles, leaving a crust primed for explosive release. Oumuamua, shorter travelled, retained its enigmatic poise without the drama. Behavioural quirks highlight the divide. Oumuamua tumbled chaotically, its light curve varying wildly, suggesting a spin induced by torque from uneven surfaces or past collisions. Atlas shows subtler photometry, perhaps a steadier rotation every few hours, implying structural integrity despite its bulk. Oumuamua exhibited that mysterious acceleration, about 5 times 10 to the -6 meters per second squared, hinting at invisible outgassing, maybe hydrogen from irradiated ice. Atlas, with its Goliath mass, shrugs off such influences. No detectable wobbles mar its hyperbolic grace, raising questions about internal damping or a monolithic core. Discovery contexts mirror their personalities. Oumuamua emerged post-perihelion, already outbound when pan-stars caught it, limiting study time. Atlas, inbound when Atlas, the survey, not itself, nabbed it, grants us months of prep. Hubble and Webb already dissecting its coma, with more revelations expected. Oumuamua's post-flyby fade left regrets. We missed probing its depths. Atlas invites thorough scrutiny, its size promising richer spectra and perhaps radar bounces for shape mapping. Speculative threads weave through both. Oumuamua ignited extraterrestrial tech theories, its shape like a light sail, acceleration like thrust. Atlas amps that with mass anomalies and metal quirks, some pondering if density hides hollow chambers or engineered density. Mainstream views favor nature, Oumuamua as a hydrogen iceberg fragment, Atlas as a carbon-rich planetesimal from a red giant's shed. Yet the what-ifs persist. Could both be probes, one stealthy, the other bold. Implications ripple outward. Oumuamua reshaped detection protocols, birthing surveys for more interlopers. Atlas, with its heft, probes formation in thick disk nurseries, where metal-poor stars forge oddballs, comparing them spotlights diversity. Slender speedsters versus bulky bruisers, each sampling galactic flavors. If Oumuamua was a whisper, Atlas is a roar, demanding we rethink interstellar populations. Future echoes loom. Oumuamua recedes toward Lyra, forever lost. Atlas heads Gemini ward, but its mass might leave gravitational fingerprints on distant objects, traceable later. Both underscore our system's openness, gateways to galactic exchange. In this cosmic matchup, Oumuamua embodies subtlety, a fleeting puzzle that slipped away. Atlas demands attention with its girth and glow, a heavyweight challenger rewriting rules. What binds them? The thrill of the unknown, each a breadcrumb from afar, teasing at universes beyond our grasp. As Atlas nears its solar tango, Oumuamua's shadow lingers, a reminder that space holds endless variants, each more curious than the last. If you're enjoying diving into these interstellar mysteries with me, consider subscribing to stay updated on more explorations like this. Turning on notifications means you'll never miss the next cosmic revelation. Venturing into the realm where cosmic drifters collide with human curiosity, let us juxtapose the enigmatic profiles of 2I divided by Borisov and 3I divided by Atlas, two interstellar comets that, despite sharing the rare badge of galactic outsiders, diverge in ways that tease at the universe's hidden recipes for forging such wanderers. Borisov, unveiled in the late 2010 seconds by an amateur stargazer peering through a homemade telescope in Crimea, emerged as a classic yet alien comet. A fuzzy nucleus sprouting a tail of cyanide and diatomic carbon, 2000 a veil of Rule. Its hyperactivity driven by an unusually high carbon monoxide content that made it puff like an overzealous smoker approaching the Sunday. Spanning perhaps 0.4 to 1 kilometre, it was modest in stature, a lightweight traveller at around 32 kilometres per second, looping in at a perihelion of 2.01 astronomical units, safely beyond Mars's turf, where the solar warmth coaxed out its volatile secrets without shattering its core. Now pivot to 3I divided by Atlas, this year's colossal intruder, whose sheer presence demands a re-evaluation of what an interstellar comet can be, clocking in at 60 kilometers per second, nearly double Borisov's clip. It charges through with the urgency of a messenger, bearing urgent news from the stars. Its nucleus, estimated at 0.4 to 5.6 kilometers or even broader in some models, towers over Borisov's diminutive frame, and with a mass potentially hitting billions of tons, it carries a gravitational authority that Borisov could only dream of. What if this bulk hides layers of untold history, a stratified archive of interstellar voyages that Borisov's slimmer build simply lacks the space to preserve? Borisov, for all its charm, felt fragile. Its outgassing, vigorous but contained. Atlas hints at indestructibility, its path unperturbed by the jets that might veer a lesser body off course. Consider their solar flirtations. Borisov's distant perihelion at 2.01 astronomical units allowed it a gentle warming, sublimating ices into a coma rich with carbon monoxide levels 30 times higher than typical solar system comets, suggesting birth in a frigid, carbon-laden cradle far from any hot stellar nursery. It bloomed predictably, its tail extending hundreds of thousands of kilometers, a spectacle observable from Earth with modest gear. Atlas, daring closer at 1.36 astronomical units, risks a fiercer solar embrace, potentially unleashing carbon dioxide in ratios that dwarf Borisov's excesses, 19.5, 5 to 1 against water. A brew so carbon-heavy it evokes visions of a smothered, ancient world. Might this proximity trigger a cataclysmic breakup, scattering fragments like cosmic shrapnel? Or will its mass hold firm, turning the event into a controlled fireworks display? Borisov survived intact, its stability a testament to balanced composition. Atlas's gamble could reveal fractures or, intriguingly, an inner resilience forged in harsher climes. Orbital dances reveal further contrasts, like two performers interpreting the same music with wildly different choreography. Borisov approached on a prograde incline of 44 degrees, aligning somewhat with our system's flow, a moderate tilt that eased its integration into observational routines. It waltzed in from Cassiopeia, its path a broad hyperbola with eccentricity 3.356, bending gracefully under the sun's influence without dramatic flair. Atlas, in stark rebellion. Counters with a retrograde 175 degrees, essentially backward and nearly planar, charging against the grain like a contrarian artist. Its eccentricity soars to 6.139, a sharper escape curve that minimizes solar meddling, propelling it from Sagittarius through a brisk transit. Borisov's leisurely pace allowed months of detailed scrutiny. Atlas's sprint compresses the timeline, heightening the urgency will we capture its essence before it bolts toward Gemini. Eccentricities aside, their hyperbolic excesses paint portraits of eviction. Borisov's 32 kilometers per second suggests a milder boot from home, perhaps a planetary gravitational assist, or stellar perturbation in a quiet corner of the thick disk. Atlas's 60 kilometers per second implies violence, a supernova's shockwave or a black hole's whip, hurling it with fury across the galaxy. This velocity gap raises puzzles. Did Borisov drift lazily through fewer encounters, preserving its ices, while Atlas, battered by more stellar brushes, evolved a tougher skin? Borisov's prograde path might stem from a system mirroring ours. Atlas's retrograde screams chaos, perhaps from a retrograde disk around a rogue star. Chemical tapestries weave even richer divergences. Borisov dazzled with carbon monoxide dominance, its coma laced with cyanide, hydroxyl, and hints of ammonia, a cocktail reminiscent of our Oort cloud denizens but amplified, as if dialed up by an extraterrestrial chemist. Spectra from Hubble and ground arrays painted it as a pristine relic, its isotopes skewed toward heavier variants, fingerprints of a distant formation zone poor in deuterium. Atlas counters with carbon dioxide overload, nickel vapor untethered from iron, and a dust-dominated coma glowing red elements that hint at a cooked exterior, irradiated over longer epochs. The nickel anomaly, with ratios exceeding 1 to iron, evokes synthetic alloys more than natural grains. Borisov's metals, if present, blended seamlessly without such drama. Could Atlas's excesses stem from an asymptotic giant branch star's outflows, carbon-rich winds that Borisov escaped? Or does Borisov's carbon monoxide point to a colder, more isolated birth, while Atlas endured a hotter, metal-forging crucible? Ages and origins add temporal intrigue. Borisov, clocked at perhaps a few billion years, feels relatively fresh from the galactic thick disk, its volatiles intact despite the journey. Atlas, with estimates stretching to 7 or 14 billion years in some analyses, carries the weight of antiquity potentially predating our sun, its surface etched by cosmic rays into a resilient shell. This longevity might explain the subdued non-gravitational effects. Borisov wobbled slightly from jets, its lighter mass responsive to outgassing. Atlas plows on unswayed, its billions of tons damping any thrust. What stories does that mass conceal? Accreted debris from past systems, or an inherent density from a metal-rich progenitor? Behavioral spectacles differ too. Borisov erupted into view post-discovery, its tail bifurcating into ion and dust components, a dual nature that enthralled observers. It fragmented mildly near perihelion, shedding pieces that trailed like breadcrumbs, offering glimpses into its interior. Atlas, still inbound, shows a nascent coma with hints of a tail at 3 arcseconds. But its red hue suggests dust dominance over gas, perhaps a precursor to a grander show or a sign of depleted volatiles. Will it fragment explosively, its closer solar kiss proving too intense? Or endure, as Borisov did, revealing stratified layers? Borisov's stability allowed chemical mapping down to molecular levels. Atlas's scale promises bulk analysis, perhaps radar echoes delineating a rugged topography. Discovery narratives mirror their essences. Borisov sprang from humble origins, an amateur's lens catching a faint glow, escalating to global collaboration. Atlas burst from automated surveys, its speed demanding immediate recalibrations. Borisov's Earth approach at 2 astronomical units felt distant yet intimate. Atlas's 1.8 astronomical units in December sharpens the focus, a closer shave without peril. Speculative undercurrents swirl. Borisov quashed alien tech notions with its cometary normalcy. Atlas revives them with mass anomalies and pure nickel echoes of engineered resilience, both from the thick disk. Yet Borisov's prograde calm versus Atlas's retrograde storm suggests varied ejections. Borisov, a gentle castaway. Atlas, a battle-scarred survivor. Implications cascade. Borisov expanded comet archetypes, proving interstellar kin to our own. Atlas pushes boundaries with size and chemistry, questioning population models how many heavyweights lurk undetected. Comparing them illuminates galactic diversity. Lightweight sprinters like Borisov, heavyweight chargers like Atlas, each sampling different stellar forges. As Atlas nears its trial by fire, Borisov's legacy whispers, cautions, activity can surge unexpectedly. What if Atlas's carbon dioxide brew leads to a hyperactive phase outshining Borisov's display, or reveals organics hinting at panspermia, seeds Borisov only teased? In this interstellar duet, Borisov plays the familiar tune with exotic notes. Atlas composes a symphony of extremes, beckoning us to decode its score. Their contrasts not only highlight individuality, but probe the galaxy's forge, where light comets dance and heavy ones thunder, each a clue to the unseen vastness. What other variants await discovery, bridging or widening these gaps? The cosmos, ever elusive, dangles these puzzles, urging deeper gazes into the night. Unraveling the chemical tapestry of 3I divided by Atlas is like decoding a message scrawled in an alien script. Each element and molecule a glyph hinting at forgotten stellar forges, cosmic journeys spanning billions of years, and perhaps even the raw ingredients that could spark life in distant worlds. At its core, this interstellar behemoth reveals a composition dominated by carbon dioxide, with ratios to water vapor that shatter records, clocking in at levels higher than any comet humanity has ever scrutinized. Spectroscopic data from the James Webb Space Telescope, peering through the object's hazy coma in infrared splendor, shows carbon dioxide overwhelming water by a factor of nearly 20 to 1. A brew so skewed it suggests the surface has been relentlessly bombarded by cosmic rays during its eons-long drift through the Milky Way's thick disk. What cataclysmic events sculpted this imbalance? Was it the relentless pummeling of high-energy particles stripping away lighter volatiles, leaving carbon dioxide as the hardy survivor? Or does it echo the chemistry of a parent star system where carbon reigned supreme? Delve deeper, and the anomalies multiply, each one a breadcrumb leading to questions that tug at the edges of our understanding. Nickel emerges as a star player in this molecular drama, vaporizing into the coma at rates between 10 to the 23rd and 10 to the 24th atoms per second, even when the object lingers at 2.85 astronomical units from the Sun, a distance where such heavy metals should remain locked in solid form. Yet here it sublimes prematurely, untethered from its usual companion, iron, resulting in a nickel-to-iron ratio exceeding 1. In our solar system's comets, like those probed by the Rosetta mission to 67P divided by Churyumov-Gerasimenko, nickel and iron dance in lockstep, with ratios below 0.1, mirroring the primordial disk from which they formed. Atlas defies this norm. Its pure nickel, perhaps bound in volatile compounds like nickel tetracarbonyl, a molecule that evaporates easily under mild heat. Could this be a signature of synthesis, in a carbon-rich envelope around an asymptotic giant branch star, an elderly giant shedding layers enriched with heavy elements? Or does it whisper of processes unknown, where radiation forged unstable bonds during the object's interstellar exile? The coma itself paints a vivid portrait, glowing with a reddish hue that signals dust as the dominant force over gas, a dusty shroud enveloping the nucleus, extending outward in a faint halo captured by the Hubble Space Telescope's keen eye. This red tint arises from scattering by fine particles, possibly silicates or organics baked to a crimson patina, contrasting with the bluish glows of gas-heavy comas in our local comets. Traces of cyanide flicker in the spectra, common enough in cometary outgassing, but here intertwined with the nickel enigma, suggesting cyano-nickel complexes or similar hybrids. Hydroxyl radicals appear sparingly, their scarcity underscoring the water-poor environment, another puzzle piece implying desiccation over cosmic timescales. What if these dust grains harbor complex organics, amino acids, or polycyclic aromatic hydrocarbons, the building blocks of life? Early analyses hint at such possibilities, with infrared signatures teasing at carbon chains that could have seeded prebiotic chemistry in its origin system, or, daringly, might sprinkle our own if fragments linger. Age becomes a silent architect in this chemical narrative, with estimates placing 3I divided by Atlas at 7 to 14 billion years old, potentially older than our Sun, a relic from the galaxy's formative epochs, when the thick disk swirled with metal-poor stars and turbulent gas clouds. This antiquity explains the cooked facade. Cosmic rays, those relentless high-energy protons and nuclei zipping through space, have likely penetrated the surface, inducing spallation reactions that alter isotopes and erode ices. Heavier isotopes of carbon and oxygen dominate, a fingerprint of prolonged exposure far from stellar shields. Compare this to younger interstellar kin like 2I divided by Borisov, whose carbon monoxide richness suggests a more recent ejection from a colder, less irradiated cradle. Atlas's profile evokes a survivor, its volatile, stratified outer layers depleted, inner reservoirs waiting for the sun's kiss to unleash them. Might deeper probing reveal preserved pockets of primordial material, untouched since the galaxy's youth, offering a window into conditions predating our solar system? Spectroscopy from the Very Large Telescope in Chile's Atacama Desert adds layers to the intrigue, capturing emission lines that map the coma's dynamics. The dust tail, stretching mere arc seconds in early images, could elongate dramatically near perihelion, scattering sunlight in ways that reveal particle sizes, perhaps micrometer-scale grains, laced with refractory metals. Absence of certain expected lines, like those from sulfur or phosphorus, further skews the picture, hinting at a formation environment deficient in these elements. Phosphorus, crucial for life as we know it in DNA and energy molecules, shows up faintly if at all. Does this imply a barren origin, or has it been sequestered in the core, awaiting release? The carbon dioxide hegemony might stem from clathrate hydrates' cage-like structures, trapping gases that favor carbon dioxide over others, a hypothesis supported by lab simulations of interstellar ices. Ponder the implications for astrobiology. If Atlas harbors organics, its passage could disseminate them across our system, testing panspermia theories where life hitchhikes on cosmic debris. Amino acids, detected in meteorites like Murchison, form under irradiation of ices containing carbon, nitrogen, and hydrogen, precisely the mix Atlas's spectra suggest. What if glycine or alanine lurk in its dust, survivors of the journey? Early Webb data teases at hydrocarbon stretches, broad absorption features around 3.4 micrometers, evocative of aliphatic chains. This could link to the object's thick disk roots, where ancient stars fused lighter elements into carbon-heavy outflows, seeding planetesimals with prebiotic soups. Yet, mysteries abound in the metallic realm. The nickel vapor, devoid of iron, challenges nucleosynthesis models. In stellar interiors, iron peak elements like nickel form via silicon burning in massive stars, but typically alongside iron. Atlas's imbalance might trace to a supernova's asymmetric explosion, where nickel isotopes decayed or segregated. Alternatively, cosmic ray spallation could have transmuted iron into lighter fragments, depleting it over time. A tantalizing quote from NASA's Stephanie Millam captures the essence. "This is our first deep look into chemistry from another stellar system. It's like opening a time capsule from the galaxy's past." Her words underscore the revolutionary potential. Atlas, as a probe of exoplanetary compositions, revealing how distant disks differ from ours. Dust analysis adds texture, with polarization studies from ground telescopes suggesting irregular grains, perhaps fluffy aggregates formed in low-density environments, contrasting the compact silicates in our comets. These could trap volatiles efficiently, explaining the delayed outgassing. As perihelion approaches, heating might liberate methane or ammonia, shifting the coma from red to blue-green if cyanides ionize. Will we see forbidden oxygen lines, indicators of water dissociation, or remain in carbon dioxide's shadow? Isotopic ratios offer chronological clues. Deuterium to hydrogen in water vapor, if detected, could peg the formation temperature low deuterium, suggesting a warm birth disk, high pointing to frigid outer reaches. Atlas's tentative low deuterium aligns with thick disk warmth, where turbulence mixed reservoirs. Nitrogen isotopes, 15 to 14, might reveal atmospheric escape in its parent system, a process sculpting habitable zones. Broader galactic context intrigues. The thick disk with its older wandering stars hosts chemistry diluted by supernovae remnants, enriching in alpha elements but poor in iron. Atlas's iron scarcity fits. Its nickel perhaps from neutron capture in asymptotic giant branch winds, slow neutron processes building heavy isotopes without iron dominance. This ties to models of galactic chemical evolution, where thick disk objects like Atlas serve as benchmarks. Speculation edges toward the exotic. If nickel tetracarbonyl dominates, it forms under specific pressures and temperatures, perhaps in a subsurface ocean now frozen, hinting at a watery past. Or, in wilder veins, synthetic origins, nickel carbonyl, used in earthly purification processes, echoing artificial refinement. Mainstream dismisses this, favoring natural pathways. But the anomaly keeps doors ajar. As observations accumulate, the chemical story evolves. Webb's mid-infrared instrument might soon resolve molecular bands, identifying formaldehyde or methanol intermediates in organic synthesis. Ground-based radio telescopes could hunt for maser emissions, amplified signals from hydroxyl or water, revealing hidden reservoirs. In essence, 3I divided by Atlas's chemistry is a mosaic of extremes: carbon dioxide, excess, nickel purity, dust, dominion, each tile a query about origins, evolution, and potential. It challenges textbooks, inviting revisions to cometary paradigms. What if this composition mirrors exocomet, swarms around other stars, detectable via transits, or holds keys to carbon cycles in habitable worlds? The object's passage transforms it from visitor to teacher, its molecules narrating a galactic epic we are only beginning to comprehend. As the sun awakens more secrets, the curious builds what further revelations lie in its atomic heart. Peering beneath the surface of 3I divided by Atlas unveils a labyrinth of peculiarities, where the ordinary rules of cosmic chemistry twist into something profoundly unsettling, starting with the glaring anomaly of its nickel emissions, a metallic vapor that defies expectations and ignites debates about the very nature of this interstellar intruder. Detected through the sharp lenses of the Very Large Telescope in Chile, atomic nickel billows from the object's coma at astonishing rates, churning out between 10 to the 23rd and 10 to the 24th atoms per second, even as it cruises at a chilly 2.85 astronomical units from the Sunday. At such distances, heavy metals like nickel should remain stubbornly solid, locked in the nucleus's icy grip. Yet here it evaporates like mist on a warm morning, untangling itself from the iron that typically accompanies it in natural formations. The ratio of nickel to iron soars beyond 1, a stark inversion of the norms seen in solar system comets, where nickel clings to iron in proportions less than 0.1, as if forged in the same stellar crucible. This pure nickel, unadulterated and abundant, raises immediate red flags. Is it a freak of galactic evolution, or a clue to something engineered beyond our wildest speculations? Consider the mechanics of this metallic mystery. Spectroscopy reveals emission lines at specific wavelengths, 231.6 nanometers and 341.5 nanometers, pinpointing nickel in its vaporous state, liberated perhaps from volatile compounds like nickel tetracarbonyl, a molecule that forms under conditions of high carbon monoxide pressure and moderate heat. In laboratory settings on Earth, nickel tetracarbonyl is a toxic intermediary in metal purification processes, volatile enough to boil at room temperature. Applied to Atlas, it suggests a scenario where carbon-rich environments in the object's birthplace, maybe the envelope of a dying asymptotic giant branch star, trapped nickel in these fragile bonds. As the object warms near our sun, these compounds decompose, releasing nickel gas without the iron that would normally tag along in dust grains. But why the absence of iron? Cosmic rays, those invisible assassins of space, might hold the key. Over billions of years, their relentless bombardment could have spallated iron atoms, breaking them into lighter fragments and depleting the surface layers. Alternatively, the parent system's nucleosynthesis, the stellar alchemy fusing elements, might have favored nickel through neutron capture processes, bypassing iron-rich pathways common in our galaxy's younger stars. This nickel quirk does not stand alone. It intertwines with a cascade of other enigmas that paint Atlas as an outlier among outliers. The object's carbon dioxide dominance, for instance, amplifies the oddity. Ratios to water vapor hit 19.55 to 1, far eclipsing records from comets like Hale-Bopp or even the interstellar predecessor Borisov. James Webb Space Telescope data confirms this excess, showing broad infrared absorptions that scream of a surface cooked to perfection by eons of radiation, where water ices sublimated away long ago, leaving carbon dioxide as the resilient overlord. Cyanide emissions mingle in, at concentrations mirroring the nickel output, hinting at cyanon-nickel complexes, hybrid molecules that could form in carbon-laden atmospheres. Why this synergy? Perhaps in the thick disk of the Milky Way, where Atlas likely originated, ancient stars belched carbon and heavy metals in uneven bursts, seeding planetesimals with these skewed recipes. Or, delving into the speculative, could subsurface processes, frozen reactions thawing now be at play, releasing preformed compounds in a timed revelation? Layer on the mass anomaly, and the plot thickens to syrupy intrigue. Estimates place Atlas at a mind-boggling 33 billion tons, a figure derived from its negligible non-gravitational acceleration, the subtle wobbles from outgassing jets that should nudge a comet off its predicted path. In typical icy bodies, these forces manifest as tiny thrusts, measurable in meters per second squared. But Atlas plods onward unswayed, its trajectory as steadfast as a battleship in calm seas. This implies a density far beyond porous ice rock mixes, perhaps a metallic core, dense with elements like nickel, anchors it against perturbations. As reported in recent analyses, this anomalous heft combines with other oddities to stack probabilities against a purely natural origin, with each quirk carrying a slim chance when viewed through the lens of known comets. What if this mass conceals hollow voids or structured internals, designed to withstand interstellar rigors? Or is it accreted debris from multiple systems, a cosmic snowball gathering density like a rolling stone? Toss in the retrograde orbit's extreme inclination 175 degrees, and the anomalies compound, suggesting a violent ejection from a chaotic birthplace, where gravitational tugs reversed its spin. This backward barreling increases relative velocities with our planets. Yet Atlas threads the needle flawlessly, skirting Mars at 0.2 astronomical units without a hitch. Add the red-dusted coma, devoid of expected sulfur or phosphorus lines, and one wonders, has phosphorus, vital for biological phosphates, been sequestered deep within, or was the origin system starved of it? Spectra from the Nordic Optical Telescope hint at this depletion, a chemical void that could imply a metal-poor stellar nursery, contrasting the iron-rich forges of our thin disk. Now, weave in the temporal echoes, like the tantalizing link to the wow signal from the late 1970 seconds. A brief, intense radio burst from Sagittarius, the very direction Atlas approaches from. Back then, at a hypothetical 600 astronomical units out, could Atlas have emitted a fleeting beacon, perhaps from ionized gases or exotic interactions? No direct evidence ties them, but the alignment stirs the pot. What if radiation hitting its surface triggered maser-like amplifications, natural lasers beaming signals across space, or, in bolder strokes, an embedded mechanism awakening? Mainstream astronomy dismisses this as coincidence, favoring pulsars or earthly interference for wow. But the overlap with Atlas's path projected backward places it intriguingly close in that era. These intertwined puzzles fuel a heated schism. Natural freak or artificial artifact? On the natural side, proponents invoke galactic diversity, thick disk stars with carbon excesses birthing comets laced with volatile metals, cosmic rays sculpting the rest. As one astrophysicist notes in a recent discussion, this is a major anomaly. But anomalies drive discovery, emphasizing how Borisov's carbon monoxide overload once seemed bizarre, yet proved natural. Telescopes have spotted similar nickel in other comets, but never so pure or prolific. Perhaps Atlas amplifies a rare but real process. Supernova remnants could inject nickel isotopes, decaying over time without ion buildup. Lab experiments, simulating interstellar ices, show nickel carbonyl forming under radiation, volatilizing far from stars, a plausible pathway for the observed vapor. Yet the artificial camp, led by voices like Harvard's Avi Loeb, counters with probabilistic jabs. The confluence of pure nickel, evocative of refined alloys, immense mass, suggesting construction, minimal acceleration, implying no random jets, and chemical imbalances tips the scales. Loeb argues the odds of all these aligning naturally hover at a fraction of a percent, likening it to finding a smartphone on a beach and calling it a fancy rock. In publications, he posits Atlas as a probe or relic, Its nickel, a structural component, perhaps a heat shield or antenna material, eroding now. Pure nickel emissions are highly anomalous. Echoes a community forum where debates rage over whether this mirrors engineered purity or just exotic astrophysics. If artificial, implications cascade. A civilization advanced enough to launch such a massive scout, navigating retrograde for stealth or efficiency. Sampling systems like ours, bridging these views, hybrid theories emerge. Perhaps a natural object altered by alien tech. A captured comet repurposed as a von Neumann probe. Self-replicating across stars. Or biosignatures lurking nickel enzymes in extremophiles, hinting at panspermia with a twist. Cyanide's presence bolsters this, as it forms prebiotic precursors under UV light. Perihelion looms as the ultimate arbiter, where intensified heat could crack the nucleus, exposing internals. If fragments reveal uniform density, natural wins. Layered anomalies might sway otherwise. Webb's mid-infrared scans could resolve molecular fingerprints, distinguishing synthetic from stellar origins. Ground radars might echo off a smooth surface, unnatural for comets. This nickel-lead enigma, entwined with mass, chemistry and signals, transforms Atlas from passerby to riddle. Each data point peels a layer, but uncovers more queries. Why this purity? What forged it? Natural caprice or deliberate design? As debates simmer, the object hurtles on, its secrets veiled in vapor, beckoning us to chase the truth across the void. What revelations await in its glowing wake confirmation of galactic norms? Or a paradigm-shattering hint that we are not alone in crafting wonders from metal and ice? The curious swells. For in Atlas's anomalies lies the potential to redefine the stars themselves. Whispers from the void surround 3I divided by Atlas, fueling a spectrum of conjectures that blur the line between astronomical wonder and speculative fiction, where the object's origins could range from the mundane churn of stellar nurseries to the audacious handiwork of extraterrestrial intellects. At the heart of these musings lies a fundamental dichotomy. Is this colossal visitor a natural comet, sculpted by the indifferent forces of the cosmos over billions of years? Or does it harbour the hallmarks of a manufactured probe dispatched from a distant civilization to traverse the galactic expanse? To navigate this terrain, one must weigh the evidence piece by piece, allowing each anomaly to build a case while leaving room for the unknown, to breathe life into the improbable. Begin with the naturalist perspective, grounded in the vast machinery of galactic evolution. Proponents envision Atlas as a primordial fragment from the Milky Way's thick disk, a region teeming with ancient stars, where turbulent gas clouds and gravitational upheavals routinely eject icy bodies into the interstellar wilds. Picture a red giant star in its asymptotic giant branch phase, swelling to enormous size as it fuses helium into carbon and oxygen, shedding outer layers in stellar winds rich with heavy elements. In such an environment, planetesimals could accrete from carbon-laden debris, forming comets with skewed chemistries like Atlas's carbon dioxide overload and nickel excesses. Cosmic rays, bombarding the surface during its multi-million-year drift, would erode volatile, preferentially leaving behind resilient compounds, explaining the high carbon dioxide to water ratio and the premature sublimation of nickel tetracarbonyl. This scenario aligns with observed galactic chemistry. Thick disk stars, older and more metal-poor than our Sun, produce outliers through neutron capture and spallation, yielding pure nickel without abundant iron. As one model suggests, such ejections occur frequently, with hyperbolic velocities like 60 km per second arising from close stellar encounters or supernova kicks, propelling these nomads across the galaxy. The retrograde orbit, a natural consequence of chaotic dynamics in a retrograde disk around a binary star system, reversed by gravitational torques. The immense mass, 33 billion tons, might stem from accretion during passage, through dense molecular clouds, layering dust and ices onto a dense core, damping outgassing effects, and stabilizing the path. In this view, Atlas is no anomaly but a statistical inevitability, a sample from the galaxy's diverse comet population, much like Borisov before it, whose carbon monoxide richness once seemed exotic, but proved a natural variant. Yet, even in this comforting narrative, cracks appear that invite bolder interpretations. The nickel purity, for instance, mirrors industrial refining processes on Earth, where carbonyl methods isolate the metal for alloys in spacecraft hulls, resistant to radiation and heat. Couple this with the lack of non-gravitational acceleration. A natural comet should wobble from asymmetric jets, but Atlas holds course like a guided missile, its mass anomalously high for a porous ice rock body. What if that density conceals an artificial framework, a lattice of advanced materials engineered for longevity? Speculators like Avi Loeb propose just that, calculating the odds of these traits aligning naturally at less than 0.2%, tipping toward design. Envision a von Neumann probe self-replicating machinery sent by an ancient civilization to seed the stars, its nickel shell eroding now after eons, releasing vapor as a byproduct of some internal process. The retrograde path could be deliberate, minimizing detection in prograde-dominated systems like ours, while targeting inner planets for observation. The anti-solar tail, recently imaged by Gemini South, points away from the Sun, unusual for dust tails, but explicable if propelled by exotic thrusters or radiation pressure on a sail-like structure. And the mass? Perhaps hollow compartments, house instruments, or replicators. The overall heft masking lightweight composites unknown to us. These ideas gain traction when considering SETI implications, the search for extraterrestrial intelligence. If Atlas is artificial, it transforms SETI from passive listening to active interception, a relic washing up on our cosmic shore. Imagine decoding faint emissions, perhaps in the cyanide lines intertwined with nickel, as modulated signals carrying data from its builders. The WOW signal from Sagittarius in the 1970 seconds aligns eerily with Atlas's backtracked path, potentially a test ping or awakening burst as it neared our system. Naturalists counter with maser emissions from excited molecules, but the coincidence stirs doubt. What civilization might launch such a behemoth, one advanced enough to harness stellar energy, fabricating probes from asteroid mines, dispersing them like dandelion seeds to catalogue habitable worlds? The thick disk origin fits. Older stars host longer evolved life, with time to develop interstellar tech before their suns fade. Hybrid theories bridge the gap, proposing Atlas as a bioengineered hybrid, a natural comet colonized by extremophiles or nanotech, evolving over the journey into a semi-sentient entity. Nickel enzymes in microbial mats could explain the vapor, while mass anomalies stem from dense biofilms or mineral accretions. Panspermia takes a directed twist. Spores, engineered for resilience, seeded via cometary vectors to propagate life. Or consider geoengineering relics. A fragment from a shattered Dyson sphere, its nickel from solar sails, adrift after a cataclysm. Probabilities play devil's advocate. Natural formation odds, while low for each trait, multiply across a galaxy of trillions of stars. Rarities become common. Yet Loeb's calculus, factoring the confluence, leans artificial. The universe is vast, but anomalies this stacked demand. Scrutiny, if natural, Atlas enriches exocomet models, predicting swarms around red giants, detectable by future telescopes like the Extremely Large Telescope. If artificial, it heralds a paradigm shift proof of others, urging interstellar missions to chase similar objects. Perihelion offers a litmus test. Natural breakup yields random fragments. Structured failure might reveal geometric patterns or uniform shards. Webb could spot artificial spectra, unnatural line widths, or polarized light from machined surfaces. Radar from Arecibo's successors might echo flat facets, not rugged terrain. Humanity's response hinges on this origin riddle. Natural, a boon for astrobiology, sampling distant chemistries. Artificial, ethical quagmires arise, quarantine it. Signal back. The December Earth flyby becomes pivotal, a chance to probe with lasers or radio, seeking replies. Cultural ripples extend. Sci-fi tropes of alien probes gain credence, inspiring art and philosophy. Religions reinterpreted as divine messenger. Skeptics demand proof. Economic booms in space tech follow, funding interceptors like Project Lyra. Ultimately, Atlas's source comet or craft mirrors our own quest for meaning. Natural underscores cosmic kinship. Artificial affirms companionship in the void. As it nears, the speculation swells. What if it's neither a quantum oddity or multi-dimensional bleed? The enigma endures, a celestial Rorschach test projecting our hopes and fears onto the stars. As the cosmic clock ticks toward perihelion in late October, the scientific community braces for a symphony of revelations from 3I divided by Atlas, with instruments across the globe and in orbit poised to capture every flicker of its enigmatic behavior. A prelude to observations that could redefine our grasp of interstellar visitors. The James Webb Space Telescope, orbiting at the L2 Lagrange point, stands as the vanguard. Its mirrors already attuned to the object's infrared glow, probing depths that ground-based scopes can only dream of. By mid-October, as Atlas dips to 1.36 astronomical units from the Sun, Webb's near-infrared spectrograph could unveil molecular maps with unprecedented resolution, dissecting the coma's evolution in real time. Imagine spectra blooming with new lines, perhaps methane or ammonia bursting from subsurface reservoirs, shifting the red dust dominance to a kaleidoscope of gases. What if hidden organics emerge, their signatures whispering of prebiotic chemistry forged in alien stellar winds? Webb's ability to peer through dust veils might expose the nucleus's true shape, revealing craters or fissures that hint at past traumas, like gravitational rips from a close stellar flyby billions of years ago. Complementing Webb, the Hubble Space Telescope, veteran of countless cosmic portraits, will pivot its gaze for visible and ultraviolet snapshots, tracking the tail's elongation as solar heat intensifies. Hubble's archives already hold early images of the faint coma at 3 arcseconds. Come perihelion, that tail could stretch to arc-minutes, a luminous streak visible from dark sky sites. Ultraviolet filters might catch ionized gases, like oxygen or carbon ions, flaring in response to solar wind clues to the object's magnetic interactions, if any. Does Atlas harbor a weak field, induced by its metallic content, shielding it from particle erosion? Such data could illuminate why its nickel vapor persists, perhaps trapped in magnetic bubbles that prevent dissipation. Ground teams plan coordinated campaigns. The Very Large Telescope in Chile, with its X-shooter spectrograph, will slice the light into elemental fingerprints, hunting for rare isotopes that peg the age more precisely. Deuterium enrichments, signaling a cold birth, or carbon-13 spikes from supernova infusions. Beyond established giants, emerging observatories join the fray. The Vera C. Rubin Observatory, nearing first light in Chile, could sweep wide fields for any fragments. If Atlas fractures under thermal stress, a scenario modeled with a 10% probability, given its closer solar approach than Borisov's. Rubin's legacy survey of space and time might catch micrometeor trails from shed dust, intersecting Earth's orbit years hence. In space, the European Space Agency's Gaia mission, mapping stellar positions, could refine Atlas's backtracked path, pinpointing origin candidates among thick disk stars, perhaps a specific red giant whose spectra match the comet's carbon profile. What if Gaia's astrometry reveals subtle perturbations, echoes of past planetary encounters that altered its course toward us? Radio telescopes enter the equation, scanning for unnatural emissions that could tip the scales toward artificiality. Arrays like the Green Bank Telescope or the Atacama Large Millimeter Array will listen across frequencies, from gigahertz water mazes to low-band anomalies akin to the WOW signal. If nickel vapor ionizes, it might produce narrow-band spikes, natural synchrotron radiation, or, intriguingly, modulated carriers bearing data. SETI protocols activate here. Any repeating patterns trigger alerts, cross-checked against solar flares or earthly interference. The Allen Telescope Array, dedicated to extraterrestrial hunts, plans continuous monitoring, its beams tracking Atlas's position with arcsecond precision. Amateur networks amplify the effort, democratizing the watch. Apps like Sky Safari integrate ephemerides, allowing backyard astronomers to log brightness variations, crowdsourced photometry that refines models of rotational period, perhaps every 4 hours based on preliminary dips. What surprises might emerge from these grassroots eyes? A sudden flare, unseen by pros, could signal outgassing bursts, revealing internal pockets of volatiles. Post-perihelion, as Atlas recedes toward its December Earth flyby at 1.8 astronomical units, opportunities peak for multi-wavelength synergy. NASA's SphereX mission, if accelerated, could map the entire sky in infrared, contextualizing Atlas against background sources, isolating its glow from zodiacal dust. Ground radars like those at Goldstone might ping the nucleus for echoes, mapping surface roughness. Pitted ice suggests natural erosion. Smooth facets could fuel speculation of machined origins. If density gradients appear uneven, it bolsters the massive core hypothesis, perhaps a metallic heart explaining the stability. Looking farther, intercept missions loom as the ultimate ambition craft dispatched to rendezvous, sampling the coma or even landing on the nucleus before it escapes forever. Project Lyra, conceived for Oumuamua, revives. Nuclear thermal rockets or solar sails could chase Atlas at its outbound velocity, closing the gap in years rather than decades. Imagine a probe like OSIRIS-REx dipping into the tail, scooping dust grains laced with nickel lab analysis, revealing isotopic anomalies that confirm thick disk birth or, daringly, artificial isotopes from fusion reactors. Cost estimates hover at billions. But international consortia, NASA, ESA, CNSA, mull feasibility, with laser propulsion from Breakthrough Starshot, accelerating tiny gram-scale probes to 20% light speed for a flyby snapshot. Private ventures inject innovation. SpaceX's Starship could loft interceptors, its reusability slashing costs. Blue Origin or astroscale pitch, debris capture tech, repurposed for coma sampling. What payloads? Mass spectrometers for real-time chemistry, cameras for high-res morphology, even drills if landing proves viable. Risks abound. Hypervelocity impacts with dust could shred probes, or radiation from the nucleus, if anomalously high fry electronics. Theoretical advancements tie in. Simulations using supercomputers model perihelion stresses, predicting if the 5.6-kilometer nucleus splinters, creating a meteor stream for future showers. If intact, its outbound path offers long baseline astrometry, refining galactic dynamics, mapping dark matter halos through gravitational lensing effects on background stars. Educational outreach evolves the narrative. Virtual reality sims let users fly alongside Atlas, experiencing its retrograde whirl. Planetariums project real-time tracks, fostering public engagement. Citizen scientists reporting sightings via apps, contributing to light curves that detect spin changes. Challenges persist. Solar conjunction in November might blind optical scopes, relying on radio for continuity. Weather at ground sites could obscure key moments, underscoring space-based assets' value. Future scopes promise more. The Nancy Grace Roman Space Telescope, launching soon, could image Atlas in wide fields, capturing context with exoplanets. Ground giants like the Giant Magellan Telescope resolve finer details, spectra slicing to atomic levels. If artificial, protocols shift. Quarantine orbits for samples, international treaties governing contact. Natural or not, Atlas catalyzes tech leaps. Advanced propulsion for chasers, AI for anomaly detection in surveys. As December nears, the Flyby becomes a global event. Live streams from observatories, apps alerting optimal viewing, brightness peaks at magnitude 8. A faint gem in binoculars, its tail perhaps arcing like a celestial brushstroke. Beyond, as Atlas fades toward Neptune, legacy missions envision probes hitching rides on outbound craft, like Juice to Jupiter, detouring for slingshots. Decades hence, interstellar telescopes could revisit it, light years out, checking for activity. This observational odyssey, from Webb's infrared whispers to intercept dreams, transforms Atlas from enigma to catalyst, probing not just its secrets, but our capacity to pursue them. What vistas await? Organic treasures confirming panspermia, or signals rewriting history? The curiosity burns, for in chasing Atlas, we chase the universe's untold chapters. Reflecting on the odyssey of three, I divided by Atlas as it carves its hyperbolic path through our solar system, one cannot help but feel a profound shift in perspective. A reminder that our blue marble is but a speck in an ocean of stars, where visitors like this interstellar giant challenge the boundaries of what we deem possible in the grand cosmic narrative. This object's mere existence, hurtling from the thick disk of the Milky Way with a velocity that defies our local norms, underscores humanity's humility. We are not the center of the universe, but rather latecomers to a story billions of years in the making. Its arrival prompts a cascade of questions that extend far beyond astronomy, touching on philosophy, biology, and even the essence of intelligence itself. What does it mean for a rock, or perhaps something more from another stellar realm, to grace our skies? In its wake, Atlas leaves not just a trail of dust and gas, but a doorway cracked open to the unknown, inviting us to ponder the implications for life, technology, and our place among the stars. At its core, the significance of 3I divided by Atlas lies in its role as a bridge between worlds, a tangible link to the chemistry and dynamics of distant star systems that we might never visit directly. Consider the chemical quirks we've uncovered, the overwhelming carbon dioxide dominance, the pure nickel vapor devoid of iron companions, and the red-hued dust coma that speaks of eons under cosmic ray assault. These elements are not mere curiosities. They offer a snapshot of galactic diversity, revealing how planetesimals form in environments vastly different from our protoplanetary disk. In the thick disk, where ancient stars pulse with carbon-rich outflows from asymptotic giant branch phases, Bodies like Atlas could be commonplace, ejected during stellar death throes or gravitational brawls in binary systems. This insight reshapes our models of exocomet populations, suggesting that carbon-heavy wanderers might swarm around older stars, detectable perhaps by future transits in surveys like those from the Plato mission. If Atlas's isotopes skewed toward heavier variants confirm a supernova-influenced birth, it provides a benchmark for understanding elemental enrichment across the galaxy, tracing how heavy metals seed new generations of planets and, potentially, life. The astrobiological ramifications stir even deeper curiosity. What if the organics hinted at in Webb's infrared absorptions, aliphatic hydrocarbons or polycyclic aromatics, represent the raw stuff of biogenesis? Panspermia theories gain fresh vigor. Microbes, or prebiotic molecules, hardy against radiation in nickel-laced ices, could hitch rides on such nomads, disseminating the seeds of life across light years. Imagine Atlas as a cosmic pollinator. Its fragments, should it fragment near perihelion, scattering into the Kuiper belt, where future collisions embed interstellar chemistry into our system's edges. This blending of galactic heritages could explain anomalies in meteorites like ALH 84001, with its debated microfossils, or the organic richness of Ryugu samples from Hayabusa 2. If phosphorus, scarce in Atlas's spectra, hides deeper, it might emerge post-heating, linking to phosphate-based life forms elsewhere. The curious builds. Does this imply life is ubiquitous, evolving in carbon dioxide-rich worlds around red giants, or that our water-centric bias blinds us to alternative biochemistries? Technological echoes resonate equally profoundly. The object's stability, its unyielding path, despite potential jets, mirrors engineering challenges in our own probes, like Voyager's enduring trek into the heliopause. Atlas's mass anomaly, 33 billion tons packed into a 5.6-kilometer frame, inspires materials science. What natural composites achieve such density without collapse? Nickel tetracarbonyl's volatility could inform volatile storage in deep space missions, preventing fuel loss over millennia. If artificial interpretations hold water, pure nickel as alloy reminiscent of heat shields, the implications explode. Advanced civilizations might litter the galaxy with durable scouts, their tech evolving from carbon-based nanostructures. This spurs innovation. Laser sails for interceptors, drawing from breakthrough starshot, or AI-driven analyzers for real-time anomaly detection in surveys like Pan-STARRS. Economically, it catalyzes investment, billions funneled into space tech, from antimatter drives conceptualizing chases to quantum sensors probing faint fields. The retrograde orbit's efficiency in evading detection? A lesson for stealth satellites, minimizing gravitational signatures. Philosophically, Atlas confronts our solitude. In a universe of 200 billion trillion stars, its visit whispers that we are not alone in complexity, whether through natural marvels or intelligent design. If natural, it affirms the cosmos's creativity, birthing diversity from chaos. If crafted, it demands re-evaluation of Fermi's paradox. Where are they? Perhaps everywhere, in disguised forms like this. Cultural narratives shift. Myths of sky gods gain scientific veneer. Art depicting Atlas as harbinger of unity. Religions interpret it as divine sign, bridging faith and empiricism. Ethically, if biosignatures appear, quarantine debates arise to protect Earth's biosphere from alien microbes, or embrace exchange. Societally, it fosters global unity. Observatories from Chile to Hawaii collaborate. Data shared in real time via AirXI floods. Public engagement surges apps tracking its glow. VR sims immersing users in its journey. Education transforms. Curricula incorporate Atlas for STEM, teaching orbital mechanics through its hyperbola, chemistry via nickel quarks, inspiration ripples to underrepresented fields, drawing diverse minds to astronomy. Looking ahead, Atlas heralds a new era. With Rubin spotting dozens yearly, interstellar studies become routine, catalogues building to map galactic flows. Missions evolve interceptors by 2035, sampling returns, decoding origins. If signals emerge, contact protocols activate, humanity's first dialogue with the stars. Yet, uncertainties linger, fueling endless curios. Will perihelion reveal fractures, exposing a core of wonders, or confirm mundane ice? The December flyby, at 1.8 AU, offers our closest gaze magnitude 8 tail arcing like a question mark in the night. As it fades toward Gemini, its legacy endures. A call to explore, to question, to connect with the vastness. In closing, 3I divided by Atlas is more than an object. It's a mirror reflecting our aspirations, a catalyst for discovery that opens windows to universes within and beyond. Its passage reminds us, the cosmos invites, full of mysteries waiting to unfold, ready or not. The stars beckon. As Atlas recedes, its meaning crystallizes, a reminder of transience, urging us to seize moments of cosmic connection. The universe, through this wanderer, extends an invitation to look, learn, and leap into the unknown. What awaits in its fading light? Only time and our pursuit will tell. And if this journey has sparked your curiosity about the stars, I'd love to hear your thoughts in the comments below. Share what fascinates you most about Atlas, and don't forget to hit that like button if you want more deep dives into space's enigmas.